Hey everyone, and an absolutely huge welcome to all the focus learners joining us for this explainer. If you're the kind of person who loves digging into the actual nuts and bolts of artificial intelligence to see how the future is being built, well, you are in the exact right place. Today, we're looking at something that is, honestly, a real game changer. We are exploring this groundbreaking new concept called Recursive Language Models, or RLMs. This comes straight from a newly published 2025 paper and an open-source GitHub repo by Alex Zhang and the brilliant team over at the MIT OASYS lab. If you have ever felt the painful, frustrating limitations of AI memory, and let's be real, we all have, what we're about to look at literally changes the entire game. Okay, let's quickly dive into our roadmap for today. First up, we'll look at the LLM memory problem. 2, we'll meet recursive language models. 3, we'll break down how the magic works. 4, hands-on setup and code. And finally, 5, performance, costs, and future. All right, let's jump right into section 1, the LLM memory problem. So picture this. How do you feed a 500-page book, or worse, a massively complex enterprise codebase, into an AI? Up until now, you've probably tried pasting it all in, only to be instantly smacked in the face with that dreaded, soul-crushing context window exceeded error, right? Standard large language models just have a fixed memory limit. If your data is too big, the model just straight up crashes or refuses the prompt. It's kind of like trying to pour a whole gallon of water into a tiny little shot glass. It's just not going to work. And this brilliantly illustrates the difference in how we approach that problem. Over on the left, you've got your standard LLM trying to swallow the entire massive prompt all at the exact same time. The whole text has to fit into its active memory, which, as we know, leads to those inevitable crashes. But look at the right side, the RLM approach. It acts as this plug-and-play inference library that basically externalizes the context window. Instead of trying to hold the whole giant book in its head at once, it treats that massive prompt as an external environment that it can just interact with. Which brings us to section 2, meet recursive language models. So what exactly is a recursive language model? Well, by definition, it's a task-agnostic inference paradigm. That basically just means it can be applied to pretty much any kind of problem you throw at it. RLMs allow a standard language model to programmatically examine, decompose, and then recursively call itself over the input. And this introduces a truly incredible concept called Inference-Time Scaling. Basically, the model doesn't just need billions of more raw training parameters to get smarter. Instead, it gets better at solving complex, massive problems simply by spending a little more time thinking and breaking the data down into smaller subcalls. If that technical definition feels a bit dense, don't worry, this analogy perfectly clears it up. Think of a standard LLM as the book memorizer. You hand it a giant textbook, and it frantically tries to memorize every single word in 1 second before answering your question. And predictably, it usually crashes. An RLM, on the other hand, is like the library researcher. When you ask an RLM a really complex question about a massive text, it stays calm. It looks up the table of contents, flips to a specific chapter, reads a small snippet, takes some notes, and if it needs more help, it essentially delegates the work by calling a sub-researcher, which is a sub-LLM call, to investigate further. It's parsing the data smartly instead of just brute forcing it. All right, let's get into the technical weeds a bit. Section 3, how the magic works. So the absolutely crucial point here is this exact 3-step sequential loop. To handle these near-infinite length contexts, the model first examines the input. Second, it decomposes the task. And third, it recursively calls itself, meaning the main language model actually spawns a sub-language model to handle a smaller chunk of the data. And then that submodel returns the answer back up the chain. It just loops through this whole process, totally bypassing those annoying context limits. And for all the developers tuning in, what's truly amazing here is how seamless the implementation is. The authors designed this to be a total drop-in replacement. You are literally just shifting from your canonical single completion call, llm.completion, to the new recursive completion call, rlm.completion. That's it. The RLM wrapper handles all the heavy lifting of managing the subcalls and the state behind the scenes. Now, to execute these subcalls and interact with all that data, the RLM offloads the context as a variable inside a REPL environment. A REPL is just an interactive programming sandbox, and the GitHub repo natively supports a bunch of them out of the box. You've got your local default environment and Docker, which run non-isolated on your host machine. You have IPython, and for fully isolated cloud-based sandboxes, it supports Modal, Daytona, E2B, and Prime. Just a quick heads up though, the docs do mention that Prime sandboxes are currently in beta with a known open issue regarding slow runtimes,
But hey, actually scratch that. It's a beta for a reason, right? The overall flexibility they give you here is just fantastic.
Moving right along to Section 4, hands-on setup and code.
Getting the Bayes dependencies up and running is remarkably fast. First, you just literally run pip install RLM from PyPy or use UV to spin up your virtual environment. Second, set your environment variable for your API key, like your OpenAI API key. And finally, just run your first RLM query. The library supports all the major clients like OpenAI, Anthropic, OpenRouter, Portkey, and even local models via VLLM. Running the query gives you console output, but more importantly, it generates a log file of its trajectories, which are the exact step-by-step actions it took to get your answer.
Now, what's really interesting about this slide is the optional debugging tool the MIT team included. When you pass an RLM logger during your completion call, it writes your run configuration and every single iteration to a .jsonl file. You can then run their RLM visualizer locally using Node.js and a Shadcene UI. You just pop your saved log files into the web app and boom, you can visually debug the AI's step-by-step logic. You can see every piece of code it executed, every single sublanguage model call, and the root model calls. It takes this incredibly complex recursive process and makes it entirely transparent. All right, let's wrap things up with Section 5, performance, costs, and future. Because guys, this isn't just a cool theory. According to the actual paper, RLMs, and I quote, dramatically outperform the quality of base LMMs and common long context scaffolds across 4 diverse long context tasks. This completely validates the idea that taking the time to recursively decompose a task doesn't just bypass memory limits, it actually gives you much higher quality, more reliable results than standard models that just try to digest everything in one giant gulp. And the scale of what this unlocks? It's staggering. 100. The researchers found that RLMs can successfully handle inputs up to 2 orders of magnitude beyond standard model context windows. That is literally 100 times the amount of data standard models can handle. It fundamentally solves the context bottleneck. So to summarize the ultimate value proposition from the paper, RLMs can handle near infinite length contexts. They beat out base models on complex long context tasks. And, incredibly, because you're making smaller, highly targeted subcalls instead of blasting massive walls of text into an API over and over again, the cost per query is actually comparable or even cheaper. Plus, the whole thing is open source and actively maintained by the folks at the MIT OASYS lab. You're getting better performance on massive datasets for sure without burning through your API budget. I want to leave you all with this pretty powerful thought. We have essentially just shattered the memory ceiling. Through inference-time scaling and recursive subcalls, language models can now parse entire libraries of text and endless lines of code without crashing. So, if models can now essentially think infinitely, what on earth will they build next? And more importantly, how are you going to use this plug-and-play architecture in your own projects? Thank you so much for joining me and diving into this explainer today. Make sure you go check out the repository, play around with the visualizer, and keep exploring. See you next time.